Let's go over RNNs in more detail. So a recurrent neural network needs to keep state. That's why it's a sequential model. It takes, in addition to the weights theta that we're learning from the network, it has to incorporate a model of what state it's in, which we're going to call h. This h is just represented as a vector such that for each respective dimension, meaning each of the individual units in our network, we're going to keep a subset of parameters that are associated with those that are encoding the state of that unit. We can randomly initialize all of these parameters and think of it as a long vector where we're concatenating all of these different h's together. Once we have this h, we can tune it using backpropagation to fine-tune how the state should be kept as we go through multiple sequences. We're going to process a sequence of inputs by applying the idea of the recurrence formula at each time step. So here we are trying to determine what the new updated h is, h prime is, as a function of the previous h and the inputs. So you can see here the h would come from a previous time step, for example the ones here. Our inputs would come from a current time step from here. And that in any one of these nodes, for example this node here, we have the inputs that are coming from the bottom as well as the previous state that comes from the node's previous version of itself in the previous time step. So it's important to note, as we did in the pre-lecture, that these weights are shared. We're only optimizing a single set of weights for all of the time steps. So all of the purple edges here would be the same even though we would have it unrolled for multiple time steps. So what we're going to do is process a sequence of inputs by applying the recurrence formula at each time step. So here what we want to do is take the current state that we have and use it to compute the next state. We're going to do that by taking a function of the previous state and the inputs at the current state, and then passing that through a nonlinearity to get the current state. Just like what we are doing in a CNN is we are trying to do weight tying, such that we use fewer parameters to come up with a model that's expressive and encodes what regularities we want to see. That is, that the current state depends on the previous state. So we're going to share the same set of weights for all of the time steps. For example, all of these purple edges that you see here, the weights for these edges are going to be reused again for the time step at x3 all the way to the last input in the sequence. When we have a state, then we have to create 3 different weight sets that we're going to conserve throughout the computation. So if we want to operationalize this equation where we said that the current state depends on the previous state, we're going to have to translate it to what we have on the right-hand side. I'm going to say that the current state is basically a function of the previous state multiplied by the edge weight specific to that, as well as the current inputs x prime times the weights associated with this. Adding these two inputs together to create a single representation, our signal, and passing that through a nonlinearity, and then deriving the hidden state that is for this time step. After we have the hidden state for this time step, then we compute the output by multiplying against the current weights for how the current state influences the output. Let's run through an example for how this works. We're going to use the Stanford slides here and look at a character predictive language model, in which we might try to predict which letters would come after each other. We're going to do this over a toy vocabulary where we only want to predict one of 4 letters as output. If we give a training sequence like hello, it would be visualized, for example, down here, where each letter in sequence is being passed in the training phase to learn the appropriate weights. These might be given in a one-hot encoding so that the first dimension is a 1 if it's an H. The second dimension is a 1 if it's an E, and the third dimension a 1 if it's an L, and so on and so forth. So the size of this input layer in this case would be the size of the vocabulary being put into the network. At the hidden layer, what we're trying to do is compute the hidden state going forward. So we have some randomly initialized values at the beginning, and after taking the weights that we would learn through all of the time steps here, we would multiply that to get the hidden state for the current time step, which is a function of both the inputs at that time point as well as the hidden state coming from the previous time step. As we continue our forward pass, we're going to take the hidden state where we currently are and come up with an output. So at this point, we are going to go through a softmax layer and convert these particular output scores into a probability distribution. And we are trying to optimize this through backpropagation so that we actually know that E should be the next letter and is actually predicted properly. So notice in this particular example that E actually has only a 13% chance of being correct here as determined by our current weights. But through backpropagation, we want to tune this so that this number gets higher. At testing time, we're going to do some things a little bit differently. We're going to feed the characters in one at a time, going feed forward through the network, and then at the softmax, sampling what type of output we want. So just imagine, for example, even though we have only a 13% chance of getting it right, let's just say when we sampled, we got the letter E out here. Okay? Then what we're going to do is we're going to take this E and forward it to the next time step and continue on with this network. So basically, we are going to take the outputs of each of the time steps and forward it to the next time step. This is the case of a many-to-many RNN sequential output. So one difficulty that we have at this point is to deal with backpropagation. When we do forward propagation, we can calculate all of the outputs of our sequence. Some of these outputs would be wrong. For example, perhaps this node, this node, this node, this node, etc. These are all incorrect. So they will induce some type of loss. We're going to accumulate that in our J train. When we do backpropagation, we have to take this particular loss and shift it all the way back through the network. So we have to go all the way to the beginning of the sequence to propagate the information all the way back through the input network. This can be pretty time-consuming. What we do practically is run backpropagation, but truncate the number of states that the backprop affects. We may decide after getting the training loss here to only backpropagate through a number of different time steps. In certain deep learning frameworks, they may not enforce this window of K, but instead partition the input into blocks, in which we would still do the forward propagation all the way through, but when we do backpropagation, limit the window to that part. So even if we're here in the sequence or here in the sequence, we would only backprop to this point.